You rely on your oscilloscope every day, so selecting a new one that meets all of your needs is important. Unfortunately, comparing the specs and features of different manufacturers can be both time-consuming and confusing. We believe the following suggestions can help speed your selection process, as well as help you avoid many common pitfalls in digital oscilloscope comparisons. The first step in selecting the right oscilloscope is to match the scope bandwidth to your particular application. There's more to scope bandwidth than just the bandwidth of the analog amplifiers alone. To ensure that your new scope has enough bandwidth for your application, you need to consider the bandwidths of the signals you'll be viewing. Begin by determining the fastest rise time of all system signals to be observed. It's the rise time of those critical clock and bus lines that generate high-frequency harmonics many times faster than you expect from simply considering the signal's frequency. If, when considering a scope, you don't ensure proper scope bandwidth when looking at a signal such as a clock line, you'll see rounded edges on your scope display instead of the clean, fast edges you expected. This will affect the accuracy of your measurements and your ability to detect problems. Fortunately, there are a few simple equations to help you determine proper scope bandwidth given your signal characteristics. For example, when dealing with 1 nanosecond signal edge speed, the signal bandwidth is 500 MHz. Using the factor of 2 in the second equation with an acceptable 3% measurement error, you find the needed real-time bandwidth of the scope is 1 GHz, or even higher bandwidth is required if you need higher accuracy. So ensure that you consider a scope delivering sufficient bandwidth for your fastest signal characteristics. Another key selection criteria is how many oscilloscope channels are enough. Consider your most demanding applications as the key determiner of how many channels are enough on a new oscilloscope. Simple debug applications may require only 2 channels, while more complex debug may require 4 channels or more. As digital content dominates more of today's designs, traditional 2- and 4-channel oscilloscopes can no longer guarantee the channel count necessary to trigger on and view all signals of interest, resulting in the need for both a logic analyzer and oscilloscope. For instance, to isolate a particular cycle of a modern SDRAM, you'd need to trigger on a combination of 5 different signals: RAS, CAS, write enable, chip select, and the clock. A conventional 4-channel scope by itself is not sufficient for this basic measurement. Agilent Mixed Signal Oscilloscopes, or MSOs, seamlessly integrate 16 logic timing channels with the 2 or 4 scope channels of a typical digital storage oscilloscope. The result is a fully functional oscilloscope with up to 20 channels of time-correlated triggering, acquisition, and viewing. With 16 digital channels, any particular bus cycle of most modern embedded systems can be easily viewed or triggered on. Once bus cycles are isolated, analog channels enable you to check signal integrity or timing of all signals. Even when your focus is on more complex digital design, the MSO can bridge the gap between a traditional 2- or 4-channel scope and logic analyzer. When both a logic analyzer and oscilloscope are used, the logic analyzer only cross-triggers the oscilloscope and vice versa. This still results in a lengthy multi-step process spanning both instruments' user interfaces. On the other hand, a mixed signal oscilloscope, or MSO, allows you to do full-width triggering across both the scope and logic timing channels on a single simple user interface. So, we suggest you select an oscilloscope with ample channels for triggering, viewing, and analysis. As mentioned earlier, sample rate should be a key consideration when evaluating any oscilloscope. Sampling rate is the rate at which the scope can take a snapshot of the incoming signals. Higher sample rate translates into better real-time resolution. Most oscilloscopes incorporate a form of interleaving. This involves increasing sample rates when 2 or more channels couple their A to D converters to provide a maximized sample rate on only 1 or 2 channels of a 2- or 4-channel oscilloscope. While the banner spec of an oscilloscope may promise this maximized sample rate, it will only apply that sample rate to 1 channel. If you're in the market for a 4-channel scope, you'll naturally want access to full bandwidth on more than 1 channel. The sample rate of the scope you choose should be 4 times greater than the scope's bandwidth for capturing the high-frequency components of the signal being displayed. This particular scope only has a real-time bandwidth of 300 MHz with its 1.25 gigasample sample rate. So make sure the selected scope offers enough sample rate for the channels you want to use simultaneously. The required memory depth you need is dependent upon the amount of time you want to observe on the display, as well as the sample rate over longer periods of time with high resolution between points. A simple equation relates how much memory you'll need, given time span and sample rate. Ensuring a high sample rate across all time settings on the scope can guard against signal aliasing, as well as provide more detail when zooming into waveforms. Many users assume that the oscilloscope's maximum sampling rate specification applies to all time-based settings. Because memory depth is limited, all oscilloscopes must reduce their sampling speed as the time base is set to wider and wider ranges. The deeper the scope's memory, the more time can be captured at full sampling speed. This provides a more accurate reproduction of the input signals and increases your probability of capturing glitches and anomalies. One currently popular oscilloscope promises a sampling speed of several gigasamples per second and 10 kilopoints of memory. Unfortunately, this scope must reduce its sampling speed to a few megasamples per second when the time base is set to 400 microseconds per division and slower. This can be a major problem when operating at sweep speeds required to display a full cycle of typical RF baseband signals or long serial data streams having fast edges. Once you've determined a scope's memory depth, also check its responsiveness when using its deepest memory setting. Scopes with traditional deep memory architectures can respond sluggishly, thereby diminishing your productivity. So, when considering your next oscilloscope, be sure to check how sampling speed is affected at various time-based settings. All oscilloscope makers realize that they're simply selling pictures of your waveforms. There is no sure way to determine the best scope for your lab by specifications alone. Only by viewing waveforms of your specific design can you determine the best scope for your needs. Today's digitizing oscilloscopes fall into two broad categories: waveform viewers and waveform analyzers. Scopes designed for viewing are usually seen in test and troubleshooting applications. Here, it's critical to capture long and complex waveforms and still see the details. In these applications, the picture of the waveform gives you all the information you need. In waveform analysis applications, programs like Microsoft Windows operating systems and other advanced analysis functions apply additional levels of abstraction for determining system performance. So, select the right display capabilities for your needs. Oscilloscope triggering essentially places the point of interest or concern at the center, left, or right side of the display for viewing. While many triggering capabilities are built into today's digitizing oscilloscopes, many general-purpose users get by using edge triggering when the use of more advanced triggering capabilities could save time and effort in viewing elusive events. For example, in digital applications, it's often necessary to trigger on a specific pattern across channels. The MSO enables you to trigger across a pattern of logic and scope channels. For serial protocol designers, some oscilloscopes offer standard serial bus triggering protocols such as CAN, I2C, LIN, SPI, and USB. When you need to capture infrequent events, glitch or pulse width triggering allows you to trigger on either a positive or negative glitch. You can also trigger on a pulse greater or less than a specified width. Advanced trigger features are especially useful in troubleshooting digital designs, enabling you to trigger on a fault and look backward in time to see what caused the problem. So, we suggest you explore the breadth of advanced triggering options in any scope you consider. When it comes to probing, it's important to remember that connecting a probe to a circuit under test makes that probe part of the circuit. A passive probe tip is essentially a short transmission line, with its electrical behavior affecting both the measurement results and the operation of your circuitry. Making sure that these probe effects are within acceptable limits is critical to successful scope measurements. High-impedance passive probes offer a rugged and inexpensive solution at measurement speeds under 500 MHz, but at 1 GHz and above, which are becoming more typical, high-impedance passive probes fail to deliver the necessary signal integrity. For 1 GHz and above, active probes are a requirement. Here, we're looking at a 1 nanosecond edge with two leading 1 GHz scopes. The difference in signal fidelity is dramatic between using an ordinary passive probe and using an active probe like Agilent's 1130A Infinimax probe. Active probes, like the Infinimax probing solution, provide two key advantages over passive probes. First, active probes enable you to get full system bandwidth out of your measurement system. Secondly, Agilent active probes come with damped resistive tips to minimize for the loading effects created when connecting the probe to the device under test. Without properly damped probing accessories, a probe will load the circuit under test, causing signal ringing and distortion. Now let's look at the data. Here on the Agilent measurement system, we have the 1130A Infinimax probe with the browser tips attached. The waveform in yellow displays the original signal with 1 nanosecond edge speed before applying the probe. The purple waveform is the signal as acquired by the probe. As you can easily see, the signal as acquired by the probe is nearly identical to the original signal in yellow, indicating minimal loading effects. Comparing this to the solution with the passive probe, you see that the measurement with the passive probe results in loading of the original signal and ringing and distortion on the output signal. When compared to the original unloaded waveform, active probes provide the best signal integrity. Among active probes, the Agilent Infinimax probes do the best job of accurately reproducing the signal with no ringing or distortion. So, the key in selecting the right probe is understanding the bandwidth rating of the probe when using a variety of probe heads and accessories. Accessories meeting your physical probing configurations could cost thousands of dollars, while only degrading the performance of your high bandwidth active probe. Do you often transfer scope data to your PC? Many digitizing oscilloscopes now offer the connectivity found on personal computers, including GPIB, RS-232, LAN, and USB interfaces. This has made it much easier to send screen images to a printer or transfer data to a PC or server. For less expensive scopes that don't offer more advanced connectivity options like LAN and USB, software packages are available that allow you to easily transport the waveform images and data to a PC via GPIB or RS-232. If your PC doesn't have a GPIB card, or you want an easy way to transfer the waveform to a laptop PC, you might consider a GPIB to USB converter. If you need to connect the oscilloscope as part of an automated test system, make sure the scope comes with adequate software and a driver to suit your programming environment. Automatic measurements and built-in analysis capability can save you time and make your job easier. Digitizing oscilloscopes frequently come with an array of measurement features and analysis options not available on analog scopes. Math functions include addition, subtraction, multiplication, division, integration, and differentiation. Measurement statistics, minimum, maximum, and average, can qualify measurement uncertainty. This can be valuable for characterizing noise and timing margins. Many digitizing scopes offer FFT and jitter measurement capability as well. For power users interested in waveform analysis, manufacturers are providing greater flexibility in mid-range and high-performance oscilloscopes. Some scopes even offer software packages letting you customize complex measurements and perform math functions and post-processing directly from the scope's user interface. For example, you can write a measurement routine in C++ or Agilent V and execute it from a menu on the scope's graphical user interface. This functionality eliminates the need to transfer data to an external PC, which can save a significant amount of time for those interested in waveform analysis. So, be sure to evaluate how automatic measurements can enhance your specific applications. If our suggestions have you thinking more seriously about your next scope, then you're probably already narrowing the field of instruments meeting your more selective criteria. Be sure to take the time to evaluate each in a side-by-side comparison. Two key factors to consider in your comparisons are ease of use and display responsiveness. Ask yourself, which scope offers easy-to-use dedicated knobs for often-used adjustments like vertical sensitivity and other common measurements? How many button pushes are required to move from one operation to the next? Also, pay close attention to a scope's display responsiveness. When you change the volts per division, time per division, memory depth, and position settings, does the scope respond quickly? Try the same evaluation with measurement features turned on. Is response noticeably slower? Once careful and comparative consideration of all key issues is achieved, you should have a much better and more confident idea of which oscilloscope model meets your needs. For more information about Agilent oscilloscopes, please visit our website at www.agilent.com/find/oscilloscope.